and a PhD in electrical engineering from TU Berlin, so quite near to us today. And he started his career at Siemens and later Infineon Technologies. And among others, he built some sensor systems for biochemical sensors there. And in 2006, he joined Texas Instruments, where he is today an R&D manager for new technology development. And Mr. Brederlow has authored about 60 technical publications and holds 10 patents. And I'm quite happy to have you here today, Mr. Brederlow, because he's kind of a perfect speaker for the topic of consumer electronics and healthcare, as he has a background from TI, who has a very strong consumer electronic background, and at the same time he has a background on healthcare as well. So I'm very curious about your keynote today.
Can you hear me? Yeah, I think I need to go a little closer. Seems to be better. Okay, well, I have two challenges now. The first challenge is to basically keep you awake just after lunch. I hope I can manage this. The second challenge is I have to catch up some time. I'm typically not very good in this. So you'll see what I can do on this part. And I hope I can give you a few insights about the aspects of microelectronics. So I'm a representative of a semiconductor company. I think I can speak somehow for the driving forces in the semiconductor industry. And the first couple of slides I will be showing you. All of you who have been present in the panel will recognize. It's basically the same, so I make this very short. I just want to repeat what I've been saying at this point in time. So we have a great aging population. I can also show you now the data from US. In here, but it's the same trend in almost also highly developed countries. Well, this for the semiconductor industry means we have a big market, and the market is growing. That's a good sign. And on top of this, I think we have a challenge to really capture this market, and we want to capture the market of the health people because we want to prevent them to get ill. And we will not start at a point where the people are already ill. So that's the challenge and the vision I have in here. So from this point of view, this also means we have to take into account what these people want and what they need and what they're willing to pay for it. So healthcare infrastructure is a big issue in this context to paint a complete picture, but you have seen a lot of statements about this at this conference already. You have seen statements in the panel. There are a lot of challenges, but from a hardware perspective and from what the semiconductor industry can provide, I think everything is there. So this infrastructure is something we don't need to worry about. There's other driving forces to worry about there for sure, but they are not so much in the hardware. What I'd like to focus on is really the medical electronics. And in the medical electronics, there's two parts. And well, I would call it two sides of medical electronics which are present. One is medical imaging, medical instruments, and this is the part where really the semiconductor industry is used, and the semiconductors is used. So you get excellent images today, you get excellent processing capabilities today, but they are not driven by medical. They are driven by mostly by consumer markets today. So that's something where medical industry benefits from the progress of another industry. I think the picture is a little bit different on the left-hand side. If you talk about consumer medical devices, when we come to the same type of driving forces, consumer is a big market. This market is large enough to drive technical developments. And you can see in here we are today already have a few examples of these devices which are present, which are used every day. And I think like a blood glucose monitor is the most prominent disease which has already been used in telehealth. But others like blood pressure monitor, thermometers, insulin pumps, heart rate monitors are there today. These are the ones which are helping people who have an illness. And then there's other consumer devices like the sports shoe, where it's basically the fitness area, where people like to basically monitor their body parameters, even to share them. And these are the ones which already exist. But if you think about what we could do, if we bring also some more sophisticated medical treatments into this consumer area, then I think we are enabling from a technology perspective a big and broader market which can be used also for taking people or basically doing healthcare, not sick care. And these are just examples. There are definitely many more, and we'll go over technical challenges in this prospect in the next couple of slides. So I've already mentioned this again. There's another driving force in semiconductor industry, and that's basically the cost reduction. So cost reduction, or at the same cost, more features. That's what is driven by Moore's law. ITRS is the semiconductor industry organization doing a roadmap, and they are currently showing a second trend, which is called Moore's rule. It's basically a similar type of rule, which is if you add more features, you can and you decrease the cost. So that's basically the cost per feature is decreasing, and the amount of features or the size of the silicon stays constant. Then you can again increase the volume, and in this way drive economic growth in this market. This is something which is already happening today. However, these type of markets are more in the 130 nanometer and not in the 60 nanometer where digital CMOS products are today. So there's still a lot of room to grow into this area. The reason why this is so much behind is because there's much more integration. There's non-volatile memories, analog, passives, power, sensors, in some cases also biosensors or chemical sensors involved in this, which are integrated on the same chips. This is good for cost, but it's much more complexity. And to get there, we are lagging behind here. But on the other hand side, it's a big opportunity because we still have this potential to get costs down. Taking the markets, I think we already see today, and this is decided by media, by a market study, you see a couple of diseases which are today monitored. This is things like hypertension, diabetes, pulmonary diseases and others. And you can really see this as an exponential growth at a rather low scale. This is 1 million a year. So we have much more people on this planet than 1 million. So you can see this exponential growth can happen for some more time. So I think from all the boundary conditions, we are in a good position. So the question really now is, what is limiting us from getting further here? And that's what the rest of the talk will be about. And for this, at the beginning, I have a small vision, what I would like to see. For basically getting from sick care to health care, we need to continuously monitor data in a way that the people don't really feel about this, that they don't even think about it at this time. And for this, you need a continuously monitoring real-time device, which is doing real-time data acquisition, which is doing some intelligent data processing transmission to a place where the valuable information is stored. And in case of an urgency or in case of health is in danger, a doctor is notified, or the patient or the consumer is notified, such that he has to go to a doctor. And in this case, typically you also still have a lot of time because it's very early. And last but not least, I think people tend not to think about something which might happen. So you need to motivate the people, and the best motivation is if they don't need to care. This means low cost, and you even don't need to feel this. And this is what is shown here today. Today, patient monitoring is something like this. Someone is lying in a bed, he's severely ill, and a lot of big monitors and a lot of cables are around him to basically monitor his pulse. He's rather immobile. That's okay as long as he can't walk anyhow, but I think this is already a big improvement here for patients which are basically beyond the step of just lying in a bed. And this evolution is already happening. I think we can see these kind of systems today in hospitals, not everywhere, but they are there. But what we really need is something which is basically as small as is placed and can measure things like ECG, heart rate, temperature, activity, motion, respiration, maybe even some chemical sensing. It may have location, and it may also have a kind of interface to something which is bigger and has a good display, so that you can really take use of these data. And last but not least, it also needs to have some power. So putting power on this small plate here is rather challenging, but there are polymer batteries today which you can basically code in there. So there's nothing which is not available today. The question is more how much power is this and how long does it last? And we'll come to this later. I don't want to go into the details of different sensing principles here, simply because there's other things to talk about. This would be a talk on its own. But the typical data acquisition system for these generic portable medical systems is shown here. So this starts with an analog front end, which is basically doing the signal transition, putting these signals in the right shapes that they can be A to D converted, and then used by a processor. The processor also needs to do several other tasks, like, for example, doing user interfaces, LCD displays, like keypad, so that you have a kind of a control as a customer on this. In some cases, in other cases, you can simply do this by an RF transmission into the keypad remotely. But these two aspects need to be here. The sensor front end, the application and metrology engine, and the communication. And last but not least, there needs to be some power management, because all electronics needs power to work. And without power, this doesn't happen. Okay, so this is basically what we have. We have a sensing signal acquisition, the eyes of the system. We have a microcontroller, which is the brain of the system, and basically taking care of the threats and what is needed to add the value to the health of the consumer in this case. And then there's a couple of support circuitry, sorry, I'm too fast, support circuitry around. If you try to envision how the end customer will see this, and what does he care about? He cares about, it is easy to use, that's for sure, especially if you're talking about elder people. Elder people don't like to use the most modern gadget. You can see this on this consumer electronics trade show here. The majority of people is young. So this is definitely an important aspect. The other important aspect I'm seeing in here is it needs to be easy to wear. So it needs to be lowest weight and smallest form factor. That's the way how you can do basically put this into things like for example a ring or a wrist belt, which is there anyhow, and in this way most people don't care about this, they just see the feature. And next one is it needs to be easy to maintain, so no power charging is basically the vision. If you can do this without any recharge and this works for at least a year, that's something which makes acceptance rate high, because especially elder people, they don't think about I need to recharge this every couple of hours or every day. That's not practical. And last but not least, it needs to be very robust and fail-safe. So this means it needs to be safe in the operation under all the different application conditions, or all the different daily life application conditions an elder person can get, or long-term maybe even a younger person can get, which is maybe more challenging, because these young people are much more mobile, typically. And it also has to go through medical treatments, because we're talking about something which has to do with medical, so it needs to be fail-safe, also in a medical environment like X-ray, which is a challenge for today's microelectronics. And last but not least, I think also important, especially here in Europe, I constantly see that people are not willing to share all the data with everyone. So there needs to be a good level of privacy, so people need to be the owner of their data. And they need to give this data only to people they trust, to the doctors, not to everyone. Okay, you can derive this into different type of requirements, and this is a plot of my talk. I'll talk about accurate sensor interfaces, which is basically defining the medical data quality. I'll talk about wireless communication, which makes these systems kind of free movement to the patient, and therefore add a lot to the comfort. Then there's a small form factor is needed that is comfortable to wear, a long battery life for low maintenance, easy user interfaces for error-free use, especially for elderly people, and last but not least, data interpretation and medical treatment quality. And you can imagine that I can't give you too much dedicated comments to the later ones. I can only tell you how microelectronics can help to make this happen. Okay, let's come to the first one. I choose this as the first one because it's a good starting point and to start the story. And because in this way I can show you what the system today looks like and what the system which are available today on the market already can provide. So I'm working in a business unit which is doing low power microcontrollers. These are systems on chips. They are widely used in remote sensing applications today. You can find them in many places, maybe even in this room, I don't know. But definitely on this conference, on this trade show below. And system on chip needs to include some basic hardware functions. First of all, it needs to take care of its power regulation and clock generation on its own. For the microcontroller unit, which is basically the main digital circuit, it was acting together with the software, which is basically, from a hardware point of view, software is nothing else than more memory. And these two need to seamlessly work together to perform the tasks like the software programmer teaches the microcontroller to act. And then, on top of this, there's analog and digital peripherals, but these are supporting the application. So these are nothing else than helpers to the software engineer to make the application program better and or to reduce power consumption or to make interfaces which are not feasible just with digital circuits. That's how the system looks like, and if you look at the block diagram, then you have the clock-in power, the controller, memories, and analog digital peripherals. All communicating via the data and the address bus. Okay, well, how does this look like? This is a system on chips. This is one of our recent devices we have built. Here you see the memory, here you see the digital. This part is the core, this is digital peripherals with different functionalities. This is the power and clock generation part, and these are the A-to-D converters and analog peripherals. The total system is around about 3 by 3 millimeter. So that's already pretty small. So the microcontroller itself, even today, if you think about this is a tenth of your thumbnail. This is nothing which really hinders you from easy to wear or easy to use. So that's not a critical issue. What comes in here is a second aspect, and this is long battery life. And it's a resulting low maintenance, but you'll see also the small form factor is very much affected by this. And to get there, I will start from something which is basically a kind of a paradigm shift for semiconductor industry. And therefore, I'm starting from where the semiconductor industry is coming from. So typically, the semiconductor industry tries to increase the speed. So the benchmark is going as high as possible. And the problem with this is that we also need to go with the power high and high. So when you look at the large microprocessor unit or the regular medical equipment in there, then you're at the gigahertz range of clocking speed, but you're at the range of hundreds of watts. And basically, this is a limit, because if you want to get much higher power, then you need water cooling, and that's something which is very expensive. So therefore, speed is driven by these type of devices. This is where markets can benefit. Today, we are already approaching the next level. We are going into the watts level or 100 milliwatts level with a few hundred megahertz. In fact, these devices are currently also getting to a maximum frequency of gigahertz, but you don't need to look at the details of a daily life operation of these devices. They are typically terminally limited, so the maximum frequency in this case is a gigahertz. And if the frequency is just making the chip too hot, then the frequency is scaled down. This is how today's systems like these are working. And in this way, it's more in the hundreds of megahertz. But definitely better on power. There's something which is going to happen already. And if you look at the small consumer type electronic devices, then we're more talking about of tens of megahertz, but we're talking also about microbits of power. So there's basically 4 orders of magnitude in speed, but there's much more than 4 orders of magnitude in power consumption between these devices. And that's basically already driving a different type of technology in here. This becomes even more prominent if you look at battery capacity. So these devices, even the best one of those, have batteries like this. You can take the laptop battery. This is just one picture of this. This is how these batteries look like. If you take the portable devices, then you still have battery sizes which are this size here. And now, talking about these devices, the consumer medical devices, we're talking about a coin cell, something which is basically the battery of your wristwatch. So here, again, we have 5 orders of magnitude, basically 4 orders of magnitude in different battery capacity. If you now look at lifetime of these devices, here we're talking about a lifetime of less than a day. With these devices, we're talking about lifetimes of years, sometimes even 10 years. So this is, again, 6 orders of magnitude. So we're basically talking about 10 orders of magnitude difference in here. And that's something where we are today. And just looking at the consequences of this and how you can get there, I will spend the next couple of minutes about this topic. Starting with the battery capacity. So the battery capacity of this battery is around about 220 milliamp hours. There's a certain amount of self-discharge and charge left at the end of lifetime, so basically you can get 80% of this battery capacity. If you think that these 80% is a good average, you have around about 180 milliamp hours capacity. And this means that if you translate this into lifetime, for 1 month of operation, with this 180 milliamp hours, you can basically run 130 microamps as an average current for 1 month of operation. For 1 year of operation, you need 20 microamps. And for 10 years of operation, you can only afford 2 microamps of current consumption. So that's a challenge. We're not talking about amps, we're talking about microamps. Well, it seems to be a lot of delta, but there's a trick behind this. And this trick is shown here on this slide. So this is the logarithm of basically in the logarithmic scale, the power consumption again. And this shows you the time or what happens during an application over time. So typically, the device, after being started, gets on for a very short period of time and then consumes around about a few hundred microamp or microwatt of power. This is only for a short period of 10 to 100 microseconds, and it gets back to sleep. And in the system sleep time, which is way longer, which is around about 100 milliseconds to a second, the device basically consumes less than a microwatt. And every end cycle, typically you also have to do some more and wake up the processor for some interrupt service, for more routines, for basically making sure that this housekeeping of the system is done. In this case, you consume typically even more power because you want to do this as fast as possible, up to a milliwatt, but this is happening at even lower cycles. So now, active phases are short compared to standby times, and this is really the big trick. The active power is high compared to standby power, but if the active power time is much lower or exponentially lower time consumed in this mode than in the standby mode, then this overall concept can arise in very low power consumption overall. So on top of the active and the standby, there's also the wake-up power to be considered, because it's not easy to wake up a system this charge of only a few microamp seconds of charging. Basically, think about the one microamp second. This is nothing more than the charge you need to charge a 1 microfarad capacitor to 1 volt. So even the startup time, the startup power or wake-up power is important. And I call the last part here wireless power. The average power is just the total number of power multiplied by the number of time you're spending in the different modes. And since standby is typically 1 to 1,000 or 1 to 10,000 higher, the weight between active and standby current in the system, or the type of optimization you need to do, is basically more related to the standby than to the active mode. Classical systems are mostly or only driven by active mode, and standbys I don't care. For these type of systems, it's vice versa. And that's also why we have to choose different technologies here. Just to give you a brief idea about how the power is consumed in such a process, and I'm just talking about digital power here. The CPU, which you would think is the main contributor to the power, is only 12 milliamp per megahertz of operation. So running this device at 10 megahertz, it's 120 microamps. What is dominating here is the memory. So getting access to the data or to the code is which consumes most of the power. Other support functions here, like clock and power generation, as well as the communication overhead, is also similar range, ballpark numbers, and the CPU itself. So the system is really dominated by memory power consumption, active-wise. If you talk about sleep current, then you can see our most recent device data. So the sleep current of these devices is for sure a function of temperature, because it has a lot to do with leakage. But it's basically around about in the 300, 400 nanoamp range. So the sleep current is really low. If you think about the 2 microamp overall budget, you still have 1.5 microamp to spend in active power consumption in this case. But if you have a system which is running constantly at 80 degrees C, then you have a problem already here. And this is true for other devices as well. We have also introduced a lower power standby mode in this device, which is better in terms of leakage. However, it is worse in terms of wake-up energy, because if you need to wake up more often, then this is not a good mode. Okay, low leakage devices and power gating techniques are keys, enablers for this type of technologies. And I will show later on how this can also compare to other parts of the power consumption. But next, I'd like to come to the accurate sensor interfaces. An accurate sensor interface for these type of applications, you first need to derive what is your specification. If you look at the different phenomena we want to monitor, in fact, this is not an exhaustive list, there's a lot of things missing here, but things like body temperature, heart rate, pressing rate, blood pressure, EEG, ECG signal, maybe body sounds or musculoskeletal activity, or sometimes even audio. These are the ones we are interested in. You can see in the sample rate you need to monitor this data is pretty low. Sometimes it's hertz, sometimes it's getting up to kilohertz. The audio and the sound signals are getting up to 48 kilohertz. So basically, if you think in decades, it's 100K hertz signal. And if you look at the precision in here, also most of these applications are good enough for 12-bit. I think the only challenge in here really is the sound. The sound is faster frequency and higher precision. All the others are pretty standard devices, so you can use A to D conversion techniques here, pretty well known, and you can simply optimize them for lowest power consumption. Second issue in here is medical signals are often very small size signals, and they have a big electron offset. So if you look at, for example, at ECG and EEG and EMG, you can see, well, the frequencies we have just tackled, But if you take a look at the signal amplitudes, and you're talking here about single-digit microvolt in some cases. Sorry, the button of the beamer of the LED is too close. The LED is too close to the forward, backward. And on top of this, there's often a big offset, which can be in the orders of millivolts. And you can see the noise level. This is the 108 noise. In fact, there's also a terminal noise level in here. So we are close to the detection limit for many of those circuits. This is really the challenge for the analog circuits in here. You go close to the detection limit and you have a large DC offset. And the way how to handle this in a microcontroller device, you can really use the versatility and the flexibility of this device in this case. Because just using an algorithm and looking at the small signal, giving it the signal of guard band, as soon as you're out of the signal of the guard band, you're just adding a small DC voltage to move the system back into the right offset. In this way, with some baseline tracking algorithms, you can basically get rid of many of these large signals arising on top of the small signals. And in this way, you can then also achieve much better analog circuits because they don't need to run at much higher data rate with a much higher resolution, which typically consumes a lot of energy. So that's one way to basically tackle the problem. The other issue in here, which gives you a lot of flexibility, is the fact that you have a digital circuit on here. You have a lot of channels in here. You can basically monitor many different signals. And this is, again, something which is very interesting because think about if you not only get information about sound and body, but if you get, for example, information about chemical sensing. If you have the temperature, the chemical sensor is much more accurate than without the temperature. So if you can combine multiple sensors in one place, you have a much more powerful measuring tool for getting data which are relevant for the application. And for sure, hardware can support it. Analog in this case, what we are doing, we're building a pretty fast A to D converter, and we are switching this on and off. In this way, we are basically, it's the same principle I've shown a couple of slides back, and we can save a lot of power, and we still have a lot of resolution, and if someone needs higher speed, we can use it. So in this case, you can also sample our means at a 1.5 volt reference, a resolution of 800 microvolts. This is not enough for most of these signals, so you need to do some preamplification in here. But with an 10-to-1 preamplification, you're already good, so putting an operational amplifier to amplify the signal 10x is already something which is good enough for the application, and it needs to work in the battery voltage directly. This is showing another example. This is a chip which is also built by TI. It's the one where I have access to. This is giving you a 24-bit A to D converter for ECG. You can see this is much better resolution, 4 microvolts, has a much better cost of sensitivity. So for the high end, this is the right thing to do. This is what you can use today if you're doing ECG in the doctor's office. But on the other hand side, this is not the way how you can easily integrate this. So this is, but it is technically there. It's just a matter of the market to integrate this. Okay, now I'm coming to the two parts which, well, a semiconductor, the hardware has no direct influence on. However, I think we have an indirect influence on this, and I will tackle this a little bit as well here. And I'll start from a system level, the software aspect level of the problem of a smart medical sensor. So this is again showing the application diagram now. We are centering around how the communication of the different parts of the system are done. So again, here is the sensor on the analog front end. This is a display, a human interface like a keyboard, storage, actuator interface and a transceiver, which is basically doing communications to the bigger world or to a smartphone, tablet, computer, maybe using. And in the center, you see the processor, which is basically doing metrology, taking care of the high-level application tasks, taking care of how communication is happening, basically scheduling the communication, and who's also getting to the internal storage. Now you can see a lot of different ways of how these systems need to interact and communicate. Basically, some of this communication is bidirectional, some of this is unidirectional, or in this or that direction. And if you now look at the security and the safety aspect of this, this is rather critical. If you want to design a system which is fail-safe, you basically need to be aware of everything which can happen in the system, and you need to analyze the overall system from a system perspective for the security and for the safety. And in this case, you really need to get to every single of these different tasks and features and look for what they are good for and what you need to do to make them fail-safe or secure. And I'm just talking about security on here. For safety, it's basically very similar exercise. In some cases, it's even the same. So for example, to get data protected, you need access control. Access control from all sides, and the most prominent one is the RF interface in this case. You need to have your code separated such that only the code which is authenticated can be used, and that people cannot get into code areas which they are not allowed to get in, because then they can cause malfunction and harm, and they can steal data. You have to monitor your stored data in this way also. You have to, well, basically take care of how data exchange is done confidential. This also has to do with integrity and keys and with authentication protocols, but you need to take care of all these tasks in here. On the other hand side, you need to make sure that your system is always working as expected, and that's basically the key aspect of safety, so that's why security and safety is very close together. You need to make sure that the system is protected against malfunction. For example, if a clock is missing, that you detect that the clock is missing. In the best case, you just switch in another clock if you see the one clock is missing. Or if the power is getting too low, that you at least notify the customer, well, this device is end of life, you can't trust the data anymore. And in case of a security attack, people are trying to use these type of measures. They are doing overclocking of the system, they are running the system under voltage, and in this way they basically bring the system out of control and it gets to places where they shouldn't get to. So, to make a system secure and fail-safe, you have to prevent this to be happening. And similar things coming also in place for the peripherals. Maybe it's not as important here, but it's a big challenge also from a hardware perspective to make a system fail-safe. And together, the system is only fail-safe if the software is written correctly, but the hardware can support this pretty well. Okay, there's things missing on this slide, but doesn't matter. I think the other place where the semiconductor industry can help is makes it easy to use for the system developers. The system developer should care about the application. You should not care as a system developer about how to write an FFT, how to write a simple mass function, how to do real-time interrupt scheduling or simple decision making. These are things where low-level library can support the development very, very well, and in some cases also digital hardware functions can support this. Timers typically. You can program a microcontroller like a timer, but it's much more easy if you program a timer that it needs to start there and it needs to stop there, and then generate an interrupt, and then the software comes in again. That's things you can do to help make systems working, and I think the biggest issue typically is, well, no engineering system which is built first time is perfect at the beginning. You need to debug it. And debugging a hardware is not easy, so there needs to be a lot of help to debug. You need to find out which places things are going wrong. You need to observe basically every single register in your microcontroller. And that's where we spend a lot of effort to make these things easy. Okay, so the next is data interpretation and medical treatment quality. That's a part where I'm not an expert at all. So I need to take this as just an sidestep, and the way I'm doing this sidestep is I have to talk about memory here, because memory is one of the key parts in this context. And memory, well, without memory you don't have data. So I'm starting again from the low level. And here, just in the last couple of 1 or 2 years at TI, we have introduced a new memory technology, which is especially good also for medical markets, and I will show you why on the next couple of slides. So this is an Ephraim memory. It's not a new memory. You can buy Ephraim memories maybe almost for 10 years now from other companies as standalone memory. But we're now introducing this as a memory which is embedded together with a microcontroller. So how does it work? The difference in the working principle is very simple. You see the lattice structure of the Ephraim layer, which is a PZT layer. It's a platinum zirconium titanate with oxygen inside. And you see in the middle here there's an ion, it's a double charged ion, double positive charged ion, which can sit either in this or in that state. And basically in this way, it has a different polarization or a different charge movement. And if you place a capacitor on top and the bottom, you can show this right inside. So this is basically the ferroelectric layer. This is a plate on the top and the bottom, which is connected via transistor on the bottom inside, and via the word line, which is going this direction to the top inside. And now you can basically move this ion based on the voltages you are having in here. You can also read out the previous state by simply looking in how much charge you're getting on this line if you apply that a voltage X on this place. It will be different if the state is here or if it's here. It's in one case it's more charged than in the other case. In this way you can store information. And since the Ephraim is a non-volatile principle, so if you don't apply a voltage in here, it will always stay in this position even without power. This is an easy way to store data, and it's also an easy way to read data. And last but not least, and that's something which is very good for the semiconductor manufacturer, it's a very simple process header. So this is a normal CMOS process, this is a normal CMOS process, the materialization, this is the front end of line, the transistors, and the first connection. So you just have to add two patterning steps, the one to pattern the capacitor and the other one to pattern the via on top of the capacitor. And with these two additional mask layers, the process is non-volatile. Comparing this to existing technology and to other evolving memories, what is state of the art today is flash memory. Flash is based on floating gate transistors. Floating gate transistors are transistors which are typically taking a couple of electrons which are on a floating gate, so they cannot get away from this gate without high voltages, but they can basically over the field influence a channel up to beyond, and if the current on this transistor below is high, you have one state, if this current is low, you have the other state. That's the working principle. The problem with flash is a large writing time and therefore also a large write energy. The Ephraim, I've just explained to you. MRAM is a very similar technique to Ephraim. The only difference is it's not an electric field which is used for storing, it's a magnetic field which is used for storing in this case. Which also means that you need to read it out via a current and a change in current. This is the reason why these type of memories have much higher energy for reading and writing. The other parameters are very similar, but you can clearly see the big delta in the endurance of these devices. There's a big delta in the write energy in these devices, and there's also a big delta in the write time of these devices. So that's something which is way better, and we'll see in the next couple of slides why this is better. But before, I'd like to get to one additional point which is especially important for medical environments. This is robustness. So Ephraim is a very reliable technology. We have already seen this. It's basically infinite write cycles. If you think about 10 to the power of 15 cycles, and you think about a speed of around about 10 megahertz, you can see this is more than 10 years of lifetime. And we also have a very good data retention, up to rather high temperatures for these devices. But it is more, it is also very radiation resistant, so it's basically terrestrial software error rate you can't see in these devices. That's something which is not existing, simply because it's an ion which is storing the information and not an electron. An electron is much smaller and therefore much easier to disturb than the ion. And therefore we are also very robust against X-rays and other type of radiation with these devices, which is very good in a medical environment. Because you can basically, especially if you think about implantables later on, you need these kind of imaging techniques to get things there, but you can't do it without it. If you erase the code in this device by basically implanting it, then the reason why you have implanted this is gone. So this is something where this is really a unique difference. And last but not least, it's also secure in terms of writing data, because writing data is as fast as storing data. So if you want to change data in the system, in worst case code by a firmware update, this is something where you typically are in danger with every flash device. You can read on many instructions, please don't switch the power off. That's because in this case you can really break the system. With Ephraim, we don't need to worry about this. Okay, two practical examples. The one is data logging. If you want to log data in a system which needs to store data but also needs to store data after the power is gone, then you're very limited with flash because the write power is high and the data rate is rather low for writing data. That's something which limits the amount of data you can take. If you do this with Ephraim, you can take more data in much shorter periods of time. The other one, I've already mentioned this, is an update, a firmware update, if you want to change your software. With a flash, you consume roughly one month of battery lifetime for doing this. With Ephraim, it's a quarter of a day. And you can do this much easier because you can basically access not on a bit but on a byte level. And with flash, you basically need to have redundant mirror bank. In some cases, you even need to have redundant discharging because many microcontrollers can only discharge complete memory or nothing. And in this case, you really have trouble if you want to write code remotely. So this is something where you really can do game-changing differences. Now coming back to power consumption once again. which I think is a key part the semiconductor industry has to tackle on here, of taking a small benchmark, which is basically a typical benchmark for these medical applications. A to D converter measures every once per 250 microseconds. If you think, for example, about heart rate, about EEC is a good sampling rate, it's maybe even a little bit too high. And then evaluate these data and then get the system back to sleep. So that's basically the main function, trigger the A to D to the conversion and then get back to sleep. In some places, you don't need to do this every time because it's consuming power. If you want to basically do some more algorithms, in this case, we just simply do the averaging of all this data and then calculate the data stored into NVM. And this is basically the benchmark running, and you have to look at how much active current you're consuming. So this is the amount you need for storing the data. This is the analog state acquisition. This is the active time and the standby time. You can see in this case of frequency, the active is dominating. If you have basically lower sample rates, then this number will come down here. This now will stay low because standby time is rather low. And the interesting part here is this bar is missing. In fact, it's somewhere on here. That's because of the Ephraim. If you look at other devices, flash devices, you can see this is dominating the current consumption. And you can also see that what we are currently doing is here, we are basically bringing step functions down. We are at least 2x better, in some cases 10x, 100x better than the competition on getting power consumption down and therefore enabling lifetimes, which makes these type of products something which you don't only dream on, but you can really build from there. So this brings me to the last part. I think the wireless communication is important in the long run. It's not necessary for all these applications, at least not for the first step. But if you're going moving forward, you also need to think about wireless communication. And I'm showing you a little bit older study about what is the contribution of power to the overall system. And I have to comment this a little bit because I think I have been showing you how this can be reduced dramatically. And I think we are more in the 2 and 2% range with the most recent developments here. But what these type of systems are doing, they're constantly transmitting wireless data. Every time they take a data, they transmit it. And you can clearly see if you want to get low power, then this is not the way to go. So we have to look into different solutions in here. And different solutions. The problem here is wireless communication is a communication, and communication needs to have two persons speaking the same language. So if you're doing wireless communications, you either need to teach the other one the language, or if you want to reuse it, then you have to take a standard, because it's much more likely that the other device will understand the standards than something which you have to teach to the device. Therefore, we are relying on standards here. And these are the standards which are available today, and most of them are currently not driven by medical. You can see in here data range is typically a big issue. So we are pushing data range to 10 megabits per second. We're even talking about hundreds and thousand megabits today. But if you think about energy consumption and the amount of power you need, then you have to go just the opposite direction. We have to go this way. The other benchmark you typically find in wireless is range. Range is going, the more range the better. But on the other hand side, it's a simple it's this physics. You're propagating and you're propagating in all directions arbitrarily. If you're further away, there's a square root of distance. So you need more energy if you have more range. In the most medical applications, a 1 meter range, 10 meter range is more than good enough. So basically we are talking about this part here, and we are looking at these standards most intensively because these are the ones which are at least realistic for the type of application. Passive RFID is something which is sometimes very interesting, but I think this limits also the amount of market, because passive means also you only have power if the powering device is close to you. And this is not convenient for daily life applications. It may be convenient for blood glucose measurement. There's a place where you can do so, but it is not convenient for continuous monitoring of pulse signals, for example. So there's only a few standards which make sense, and in fact my message in here is if you want to save energy in the radio, you can do the best-in-class design, and there's definitely 2x, 3x possible compared to what is available today on these radios. You can really try to reduce your safe communication range, make it smaller. That's something you can do and which is very helpful, and some devices today also allow you to basically burn less power if you're allowing a small range. But the biggest knob you have is reducing the average on time. Why transmitting data every millisecond? Or even think about why transmitting data every second, even if you're talking about sports and fitness activity. If your data is 1 second old on your monitor, you don't care as a user. So I think this is something which is really missing today. Even the best standards on here, this is Bluetooth Low Energy, which is the one which is mostly available, which you can find in every modern smartphone today. But there's even a better one, which is currently used by the consumer, by most of the consumer watches, sports watches. This is an standard. They are, from my point of view, doing data transmission too often. So that's something where I think there's a call for action if we want to get this vision to be realized. And now I'm coming to the end of the talk. I think there's a lot of other aspects of this, and I am talking here about Continuo, which is an industry consortium which is basically driving standards for personal health devices, mostly for the interoperability of this, but also for how to deal with this in the bigger society, in the healthcare economical system. I think we have to do everything in here as a hardware manufacturer which supports this, because finally we want to make the life of the people easier and better and healthier. That's where we want to get from. And just remember the vision, this is where we are today. This is what we have to do today. If you think about the picture I've been showing you at the beginning, this is where we need to be in the future. And just talking about the solutions, there's a lot of examples today. I think we have to work on making these products much smaller, much simpler, much lower power. And in this week we can, on the one hand side, enable the large demand which allows us to make healthcare something which is affordable for the large amount of people. So it's not only a business dream, it's also a dream of a society which has more health behind this. And I think the semiconductor industry trends show you that this is possible. We have proven examples on here. This one is a more challenging one. I think the panel has shown a lot of these challenges, but we can solve these challenges, and technically we are not far away from this. I think many of these things are system-related issues, application-related issues, which we have to continue to work on this. So that concludes my talk. Thanks a lot for your attention.
Thank you very much, Mr. Brederlow, for this interesting insights to semiconductors and medical and healthcare. Are there any questions out of the audience, please?
Ralf, I actually got two questions. One, why the Ephraim actually have a higher leakage? It looks like it's showing 70 micron versus the flash, like 40 micron, something like that. The second question is, the MSP4 solution, like F59, actually that was, what, 3-4 years old. Do you have the next node would have a lower operating voltage from the Moore's law thing, and with that would be a lower power consumption? May not be the lower leakage.
Yeah. I think the first one is a good question, and I'm just looking at the right slide in here, because I think I have to explain. It was a little bit too fast, and I think this is a misunderstanding. So shouldn't do animations if you want to scroll back. So what you see in here is SRAM, not flash. Flash, in fact, is very similar to FRAM. So that's a static RAM, and the static RAM, in fact, has a lower current consumption. First of all, because this is a volatile memory, not a non-volatile memory, so you can store data a little bit more easily. And secondly, SRAM is typically designed to be very close to the critical speed issues of the technology. SRAM is specifically optimized for speed. And being close. Being close is typically low capacitance. SRAM consists only of 4 transistors, and this gives you technology difference. FRAM, on the non-volatile memory, is typically designed for density. Density means you have larger arrays, you have larger lines in between there. This is also a cost trade-off. I think you can design a lower power FRAM. It will be never as low as SRAM, simply because you also need to store data. And this always costs you something, makes your physics a little bit more complex. But the difference has to do with these two aspects. The second question was about, please help me again.
The MSP430 F59 you showing here look like it's several years old, right?
The FR59.
That's 1.8 volts.
The FR59 is in fact not a couple of years old. It's very, very new. In fact, you can only get samples at this point in time. So the leakage current of this device is in the range of 300 nanoamps. So if you talk about the older MSP430 devices, we're talking about leakage currents in a similar comparable node in the range of round about a microamp. So this is round about 3 times better than what we have been doing in the past.
How about the VDD? Still 1.8?
The VDD of these devices is typically 3.7 maximum because we directly want to attach this to batteries. Internally, the digital circuit is running at much lower voltages. In this case, it's running at 1.2 volts. This is simply because in this case you can achieve lower active energy. But this is, on the other hand side, we don't want to, we have to take care of our voltage regulation now. So there's no regulator in between. And this way we need to transfer this down.
So no LDO?
There's an LDO chip. The LDO is doing the transfer. There's a completely on-chip LDO. In fact, it's even a capless LDO, so that you don't waste energy in the wake up. So that's how it is built. And leakage, just maybe a more general comment. Leakage is unfortunately the only thing which doesn't scale well in Moore's law. It's one of the reasons why modern processors have so high problems with active power consumption. The way we are designing this process is a different one. So this process is lower leakage than the previous node. There's a lot of technical tricks in behind this. I can point you to another publication where we get more into the technical details of this. And there's a few things which we don't want to disclose at this point for sure as well as a company. But you're right, it is a challenge, but I think in this case we are going in the right direction. And we are willing to continue on this. I'm not running out of ideas how to get even better than this.
Okay, thank you.
Any other questions?
Thank you very much, Dr. Brederlow. I wanted to ask you, are the ideas of having energy harvesting in any way applicable to having these tiny devices? Could we use temperature differential, for example? And secondly, is it possible, do you think that the RF transmission power could be scaled in the future in such a way that it would become a minor part of the power budget?
Yeah, I think these are two very good questions. For the first part, I think this is really a dream. This is what I would like to have as an engineer on the one hand side. But on the other hand side, if I'm thinking about the application, which is sometimes life critical or at least need to be very reliable, the problem with all these energy harvesting sources today is that they're not reliable enough. I think the most reliable one is the solar energy, or even the inlight. We could harvest the energy in this room. This would be good enough. But even there, you cannot guarantee that someone is not in a place where it is dark for a time which is longer than this harvesting source and the storage capacitor behind this harvesting source. So you need to have at least some backup battery for this type of applications. Therefore, I'm considering this to be the second step. I think the first step is batteries, reducing battery sizes, getting lower energy circuits. You can achieve lifetimes of months, of years for still reasonable applications today. So this to me is considered to be the better starting point. Long term, for sure, harvesting is the best solution. So that's definitely one part. I again forgot the second part of the question. I'm sorry about this.
Perhaps we do that in the coffee break bilaterally because I think we are late on time. I'm sorry for that. But I think he's here in the coffee break, and I think he will join us today for the dinner. So enough time for everyone to tackle him with some more questions. So thank you very much again. And before we